This is the last lecture in the series of our discussion on magnetic ceramics. We have discussed many aspects of magnetic ceramics. In the last lecture, we were discussing about the different types of ferrites, and we are trying to give some list of the saturation magnetization or magnetic properties of some of the compounds, particularly crystallizing in the inverse spinel structure, then magnetoplumbites and then garnets. So, here are some materials of magnetoplumbites, the so called hard ferrite or hexaferrites, barium hexaferrite that has an experimental value of the magnetic moment is about 1.1 mu b. Same thing also strontium. So, both barium and strontium had a relatively low magnetic moment, but the most important thing is they are permanent magnets, their magnetization and demagnetization is difficult primarily because of their anisotropic property, its being a hexagonal symmetry structure being hexagonal symmetry. Garnet structure, as we have earlier discussed, that we have three different sites. One is the dodecahedral sites, this is the octahedral site and this is the tetrahedral site. So, there is a distribution of the three different ions. One is the iron ions and then the yttrium ion. So, in fact, two different ions, both iron as well as yttrium. The iron is distributed between the octahedral and the tetrahedral sites. The tetrahedral and octahedral sites here. Same is the case here is and only thing the yttrium has been replaced by gadolinium, and one should look at these values, theoretical value of this. One can calculate more or less following the same principle of what we have discussed for the inverse spinel structure or the ferrite spinel ferrites. This is 5 and 4.96, but if you replace yttrium by gadolinium, the magnetic moment is extremely high, much larger than anyone else. So, it is about 16 and actually one gets 15.2. So, the correlation between the theoretical value and the experimental value is quite very nice. So, these are three different types of ferrites. We have one pure binary oxides like europium oxide and chromium oxide, which also have some magnetic property. It is of a different origin of course, and but they are also useful from technical point of view or application points of view. So, this has also been listed here. Particularly chromium oxide is a very good material for tape recording purposes. Okay. Okay, that is all so far as the list of magnetic moments are concerned. Here is again we have discussed these things earlier, but it is a pictorial. This is a pictorial representation of what we have already discussed in case of ferrites. This is the antiparallel alignment of magnetic moments of the different cations. For example, if it is a Fe3O4 structure, you have Fe2 in the tetrahedral or the octahedral structure here. These two are in the octahedral structure and this is outside. So, this is tetrahedral. So, half of Fe3 plus goes to the octahedral and goes to the tetrahedral, and here it is represented like that. So, these are yellow ones are actually the octahedral sites, this is the tetrahedral sites, whereas the reddish ones are the octahedral site. So, all the octahedral sites, this one, this one, this one, all the octahedral sites are pointing upwards, whereas the tetrahedral sites are pointing downwards. So, among the octahedral sites, some of them are Fe2 ions and others are Fe3 ions. So, that is the what we call the antiparallel ordering, and of course, the blue ones are oxygen ions. So, it is because of this overlap of the p orbitals and the d orbitals of the cations and the p orbitals of the oxygen anions, this antiparallel orientation or antiparallel ordering comes up. And because the cations are of different magnetic moments, so you have a net magnetic moment, unlike antiferromagnetism. So, that is we have discussed it earlier, but this is a pictorial representation of the same. At T, but there is an important consideration here, that is the temperature dependence of the ferrimagnetism. As in case of ferromagnetism, we have a critical temperature Tc, and of course, there is a negative Tc which is something very close to nil temperature, but here this is actually the critical Curie temperature. This is Curie temperature. So, this is the relationship between the Curie temperature and the chi, that is the susceptibility. Okay. So, the susceptibility and this is related to the Curie law, and ferrimagnetism actually is prominent here. Above Tc, there is a paramagnetism, once again the reason basically being thermal vibration. So, this ordering is no longer exists, it becomes disorder, and you get a very low magnetic field, magnetization. Okay. So, that is all. The Curie temperatures of few ferrites which are of importance are like this. Fe3O4 is about 580 K, 858 K, cobalt ferrite 793 K, nickel ferrite 858 K, copper ferrite 728, and manganese zinc ferrite is about 360 to 560, just a indication of what is the Curie temperature and what is the temperature zone of their importance or practical use. Now, one thing one should also remember, that most of these ferrites are used not as a pure ferrite or pure ferrite structure, but solid solutions like this manganese zinc ferrite. So, it is a manganese ferrite and zinc ferrite put in the solid solution, and they are also having the similar properties, the ferrimagnetic properties and hysteresis loop and so on, and they are also of importance. Okay. I will give you some more examples of the solid solution ferrites. So, many of the actual ferrites are used in the solid solution form, not as a pure oxides like this. Well, with this I will just like to introduce magnetic materials in an alternating field. Ultimately, the most of these, particularly the soft ferrites, are used as electromagnets or the solenoids, and they are basically makes electromagnets using electrical field. So, their magnetic response of course changes as with the kind of variable field what one applies. So, it is the electrical current, electromagnetic interaction, electromagnetic coupling with the electrical field which is of importance. So, we must understand what exactly the alternating field does to the magnetic materials or magnetic effects. It is very similar It is very similar to what happens in case of dielectric material, and this is also the vector diagram. You have earlier you have a dielectric loss, here you have a magnetic loss. Okay, magnetic loss, you have the permeability, which is in phase with the current pulse, and this is the inductance. Okay. Here only thing is the inductance you get is not in is actually 90 degree behind, earlier in the dielectric thing. The capacitance or the current is leading the voltage by 90 degrees. In an inductor it is just the reverse. In an inductor the current is lagging the voltage by 90 degrees, and but otherwise it is more or less the similar phenomena happens. Okay. So, you have the inductance like this, the inductivity L equal to mu 0 mu r n square I by A by I, and I is the current, A is the area, and n is the number of turns we use in the coil. So, this is dependent, the total inductance is certainly dependent on the permeability of the magnetic material used. This is a kind of solenoid here, in which inside which a magnetic material is used, and depending on that will be the R and L value of the solenoid. Okay. So, earlier we had seen in the case of dielectric phenomena, the R and C are in the parallel combination, RC combination. Here is in RL combination, which is in series. Okay. And also you have a concept of complex permeability in this case, mu r star equal to mu r prime minus j mu r double prime, and you will also get a magnetic loss tan delta. Tan delta is mu r double prime by mu r prime. These are all very similar to what happens in case of the dielectric permittivity, okay, and the dielectric phenomena. So, tan delta is also a measure of loss here, similar to that. Now, why it is important, the tan delta and so on, because many of the ferrites are actually used in electromagnetic field, and electromagnetic field has a very important effect on that. Not only that, whenever you are they are used in very different frequencies, starting from low frequency to very high frequency like gigahertz and so on. Some of them are also used at frequencies of the communication purpose, that is microwaves, gigahertz. So, whenever such frequencies are interacting with this kind of ferrites, there is fair amount of loss, and one has to understand how much energy loss takes place, and what is the phase lag, because these are ultimately used in electronic circuits, electronic circuits of different kind, and in electronic circuit you have different kind of carrier waves, various frequencies, and so one has to understand how exactly they behave under different alternating fields of different frequencies. So, these are some of the additional parameters in addition to the chi, permeability and so on, the magnetic moments, but the tan delta value are also very important when you are trying to use them in different electronic circuits. So, with this background of their properties, let us again look at some of the macro properties of different magnetic materials which we have discussed so far. Some of them are ferromagnetic material and some other ferrimagnetic material. All of them have some interesting application. So, these are the properties, how they are compared. On the x axis we have plotted the coercive magnetic field, that is Hc, from the measured from the hysteresis curve Hc, and here it is the saturation magnetization, the once again from the top of the hysteresis curve. On the right you have remanent magnetization, remanent induction. So, three parameters have been used, three different parameters have been basically determined from the hysteresis curve, and for different material, different groups of material, they have been plotted here. For example, here these are cobalt based, these are metallic ferromagnets, these are different alloys. Okay. This is nickel, 70 to 80% nickel iron, because the three most important ferromagnetic materials are cobalt, iron, nickel, and many of their alloys. So, they are the most important ferromagnetic materials. So, they have been subdivided into two groups. One can see in the top the crystalline soft magnetic materials, these are called on the left, these are all soft magnets, and these are hard magnets, because the coercive field is much larger here. Okay. And this is a log scale, you can find out this is a log scale 10 to the minus 3 to 10 to the minus 10 to the plus 5. Okay. So, on this the left side is actually what we call soft magnetic materials, whereas on the hard, that is these are materials which can be used for permanent magnets. Okay. These are all permanent magnets like iron, copper, nickel, iron, cobalt, nickel here. This is iron, cobalt, chromium, and then this is a very important industrial permanent magnet alnico, and there is permalloy and so on. Here is this part is a different group of permanent magnets, which we have unfortunately have not discussed here, but these are all metallic. These are elemental, not oxides or not ceramics, but they are very important in the sense they have very high coercive field, extremely high coercive field. So, the magnetic strength, one of the highest or best quality magnetic permanent magnets one can make out of these rare earth magnets. So, neodymium iron boron, for example, this is called the rare earth magnet. There are all rare earth magnets groups. For the lower one is samarium cobalt, both of them are rare earths. So, this group here on the right, extreme right, we have the best quality magnetic material or the permanent magnets here. So, where the ceramic magnets is concerned, these are hard ferrites. This particular area is for the hard ferrites or hexaferrites. Okay. So, barium ferrites or strontium ferrite. So, this is the hard ferrite region, and one can see, although their coercive field is very high, but their saturation magnetization is fairly low. Okay. So, it is difficult to magnetize and demagnetize, but the overall magnetic strength is not that large. Okay. However, it has a tremendous application, whereas if you talk about them, the magnetization, saturation magnetization is very high saturation magnetization even for these soft ferrites. And here this is so far as the permanent magnets are concerned, these are the best quality magnets one can have. Earlier, of course, these are alnico and permalloy. These are the materials which used in as magnetic materials or permanent magnets. Now, this is the soft ferrites region, both of them, whether it is hard ferrite like this or soft ferrite like this, they have a relatively low saturation magnetization, okay, and remanent magnetization is also relatively low, right. So, they are actually related. Normally remanent magnetization and saturation magnetization are related in the sense saturation magnetization is slightly higher than the remanent magnetization. But these are the whole range of different magnetic materials we have, both in the elemental form, alloy form, as well as in the ceramic magnets. Okay. Next comparison is the different properties of ferro and ferrimagnetic materials. These are different properties. One additional property are here, that is the resistivity, the rho here. Okay. This is the resistance, electrical resistance of this material. Okay. There are three groups. One is the metals, these are the metals, the blue ones, these are ferrites, yellow ones, and the orange one are powder based material. Okay. In the powder form, what is their property? These are consolidated form, in the solid form, sintered form, whereas these are basically in the powder form, the same material when you have the powder form. So, some of the powders are also important from practical point of view. So, that is why the powder properties are also given. This is saturation magnetization by T, this is the Curie temperature, and this one is the resistance. Now, the most important in this case is the what is the resistivity value. What is the resistivity value? Because metals have a very low resistance, whereas ceramics have a high resistance, and it is this property which is much more attractive from the application point of view. This is ferrites. Ferrites have a relatively higher resistance even compared to the powders, okay, whereas metals have much lower resistance, and that causes some problems in some applications, particularly transformer applications. Okay. In transformer applications, whenever there is a low resistance, there is a phenomena called eddy current on the surface, and that depends on the particular that depends primarily on the resistance value. Lower the resistance, the eddy current is high, and therefore, there is loss is high. So, the eddy current finally gives rise to loss in the form of heat energy. So, that is the reason almost all transformer cores, if you have noticed, all transformer cores are in the laminated form, particularly the metallic cores, not the ceramic cores. Ceramic cores are solids, whereas all metallic transformer cores, iron silicon alloy in particular, which are primarily used in transformers, they are always laminated, and then they are insulated also. There is a insulating coating, resinous coating on the surface. So, they insulate each laminate from its neighbor, and that is how one increases the resistive overall effective resistance of the system. Otherwise, the eddy current loss will be so high that it will be difficult to design any transformer. Now, this problem is not there when one uses or one replaces the transformer cores with ceramic magnets, the ferrites. Because of their very high resistance, you do not need laminations, and eddy current loss is very low. Not only that, you can make miniaturized transformers, what we call sometimes spot cores, and so the total size becomes very low or very small. So, this is one of the property which has to be controlled while preparing the ferrites. Now, one also has to understand the ferrites are mixed oxides and they contain transition metal oxides. So, they have a variable valency. Therefore, any variable valency oxide has a tendency to or they have the property of semiconductivity because of the variable valency and because of the hopping mechanism of conduction and so on. So, while preparing these materials or particularly sintering at higher temperatures to make them a consolidated piece of solid, one has to control the atmospheric temperature, the environment under which it has to be sintered, because as you have seen earlier in case of discussion of our semiconductivity of oxides, it is the oxygen partial pressure which controls the charge carrier concentration, whether it is electronic concentration or hole concentration, and that in turn determines the electrical conductivity. So, if you want to control the electrical conductivity of these ferrites or mixed oxides, you have to be very careful about the sintering atmosphere. So, sintering of the ferrites or magnetic oxides is very important. Sintering atmosphere is very important to control the conductivity of this electrical conductivity of these oxides or electrical resistivity. And as I have just mentioned, the electrical resistivity one of the major consideration why ceramic magnets have an advantage over the metallic magnets. So, if you want to take the full advantage of these materials, one has to take care of the sintering conditions properly. These sintering conditions will change depending on which particular ferrite you are using, whether it is a copper ferrite or there is a nickel ferrite or it is garnet. So, all these things have to be are becoming important so far as the preparation of these materials is concerned. So, there are some intrinsic properties no doubt, but if you have to take advantage of the intrinsic properties, the preparation conditions, the extrinsic conditions have to be maintained properly. So, this is how the some of the properties of the metals, ferrites and the powders compare. Well, that is all more or less about the bulk materials. So far as the magnetic property of the bulk materials are concerned, we have a different other properties that is called magneto-resistive effect. This is a property of changing resistance of a material in presence of a magnetic field. So, there is a strong correlation between the magnetic material or the magnetic field and the electrical field. This is something related to the Hall effect, very similar. The cause is more or less arises from the similar phenomena which we see in the Hall effect, particularly in the particularly for semiconductors. In presence of the magnetic field, the resistance changes and one can find out what is the Hall coefficient, and Hall coefficient also gives us an idea which is the charge carrier, whether the negative charge carrier or the positive charge carrier. This is so there is a correlation between the magnetic field and the mobility of the charge carriers. Okay. So, one can measure the Hall mobility also. So, from that analogy or a similar kind of thing happens when you have a magnetic field is applied to a semiconductor or a conducting material, and there is a change in resistance also. Okay. So, there is a change in resistance as a result of magnetic field. So, the resistance is normally increases by a magnetic field, and that is the property is known as magnetoresistive property. For small angles of deflection, okay, that is what it takes place in the Lorentz force, which is caused by the Lorentz force, which deflects the current lines, okay, currents line within the conductor. Sorry. And thus increase the resistance. So, this small deflection, the relationship, empirical relationship is like this. The resistance R may be expressed as R equivalent to about R0 1 plus 10 QH square, where QH is the deflection, angle of deflection in presence of the magnetic field. They are important as magnetic sensors. Okay. So, these materials are of very important so far as whenever a magnetic field, just like a Hall probe measures the magnetic field. Similarly, this material also can be used as a magnetic sensor. These are some of the oxides when you talk about ceramics. These are some of the oxides which have some important or appreciable magnetoresistive effects: strontium ruthenate, thallium manganate, chromium oxide, then a lanthanum manganite, LaMNO3, which is a good semiconductor or electronic conductor, and with substitution of calcium and strontium. So, both calcium and strontium, if you remember in our fuel cell device, this kind of material is also used as a cathode material, Fe3O4, and then you have calcium copper manganite. So, these are different kind of oxides. We are not going to the details of such things, but there are quite a few oxides. There are quite a few oxides which have this kind of magnetoresistive properties and are useful for many devices. And an extension of this is called the magnetoresistive extension of this magnetoresistive effect is called giant magnetoresistance, okay, where the resistance change is much larger compared to the normal things we have which has been observed. In some, under certain situation, the resistance change can be as high as 50%, and such systems or such materials are called giant magnetoresistance, GMR materials. Sometimes it is also called CMR, the colossal magnetoresistance, CMR or GMR. So, in some cases it has been found that this effect, magnetoresistive effect, is extremely large, and they can be of tremendous importance so far as the applications are concerned. The effect is normally observed at relatively low temperatures. It is not at room temperature, relative below room temperature, and at very high magnetic field. Okay. So, whatever magnetoresistive effect has been discussed earlier, it is probably relatively low magnetic field, but when magnetic field is very high and particularly at low temperature, and the film and the materials are in the thin film forms with a multi-layer structure in particularly, then this kind of effect, a colossal magnetoresistance or giant magnetoresistance effect are observed, which is slightly different. It is not exactly the same as magnetoresistive effects in different materials. Particularly, the structure of this kind of systems is a multi-layered structures of thin films, in which two ferromagnetic films are separated, or one non-ferromagnetic or non-magnetic film is sandwiched between two ferromagnetic films. If such a film, such a material can be synthesized or fabricated, then those materials are supposed to have or has been observed to show a very high magneto-resisting effect, that is called giant magneto-resistance. In recent times there was mixed oxides with distorted perovskite structures. In fact, one of the oxides which we have discussed just now is like this. Lanthanum manganate based materials also show the magneto-resistance or the giant magneto-resistance properties. They are important, also they are also important as magnetic sensors. This is the structure, in fact this is details of what we have just discussing, the magneto-resistance effect in a multi-layered structure. So, you have a ferromagnetic, two ferromagnetic materials like cobalt film and another ferromagnetic also of cobalt, and then a non-magnetic film in between, which has been sandwiched between two ferromagnetic. So, they can be aligned, either parallelly or antiparallelly. So, based on that the resistance, the overall resistance changes. Okay. So, this is the kind of variation one expects. This is the antiparallel orientation of these two magnetic moments here, the ferromagnetic moments. Under that condition the resistance is very high, whereas if you have a parallel orientation the resistance becomes very low, like this. So, as a result of the magnetic field the resistance changes, and as a result of the magnetic field this kind of orientation external, when we apply an external magnetic field the orientation gets changed, and because of the change in orientation there is a resistance of this system. So, the GMR is normally expressed, this is the kind of coefficient which determines the extent of GMR. It is very simple, the higher value minus the lower value by the lower value. Okay. So, that is another effect so far as the magnetism is concerned. Well, this is just an example of some of the, we may come to that later, but this is only an example of thin films, magnetic materials in data storage devices, hard disks particularly, and a very simple thing, just an example of application of magnetic materials. The particle polarization, that means the thin films are getting polarized or depolarized, magnetically polarized or depolarized by applying a small magnet over there, that is the main magnet, and the disk rotates, and depending on the magnetic field generated by this magnet, electromagnet, either you depolarize or polarize them in the vertical direction. That is the structure or the microcrystalline structure of those materials, the domain structure. You have to control the domain structure of the film. So, this becomes one domain and there is another domain, and they can be either vertically polarized. Okay. So, by changing the of course, the domains must be controlled, the domain size must be controlled, domain directions, their anisotropic property must be controlled in such a way that they actually get polarized in the vertical direction. That is how we increase the overall efficiency. So, this is a very simple schematic of what happens in a magnetic disk, okay, data storage device. So, it is basically in the form of a binary system, either polarized or depolarized. Well, with this little background, I will just list out some of the applications of magnetic ceramics. Ceramic magnets have become the integral part of human endeavor. There are thousands of different systems available or devices which uses ceramic magnets. They are used in many different sectors of industry, where thousands of devices and components are used on a regular basis. Okay. Some of these things are listed here. The list is not really exhaustive. We have many different things one can think of. So, the electronics and telecommunication area, including space, defense, industrial as well as consumer electronics. So, today's electronics, even microelectronics cannot be thought of, or one cannot think of microelectronic devices without a ceramic magnet. Okay. That thousands of different kind of devices have been designed and being used extensively. Computers and data storage, one example I just mentioned, how the data storage device, the compact discs work using the magnetic property of some of these important oxides. The instrumentation and control, once again all electronic instruments and controls uses different kind of magnetic materials, either as a miniature transformers or miniature motors. Okay. For miniaturization, such kind of magnetic materials are very important, and as I mentioned already that they have a very low eddy current loss. So, the overall loss is very low. In telecommunication, microwave is one of the major area of telecommunication, and there is a huge range of microwave ferrites. Microwave ferrites are normally the garnets. The garnets which we have discussed earlier, they are the microwave ferrites. Of course, spinel ferrites are also used, but microwave ferrites are certainly the garnets are primarily microwave ferrites or used as microwave ferrites. Automobiles are aerospace area, automation and robotics, energy harvesting and storage, and medical diagnostics and cure. Okay. Medical diagnostic, NMR and so on, Magneto-resistance, the nuclear magnetic resonance is one of the techniques to diagnostics. We have discussed this to some extent in terms of while we are discussing about the superconductors. So, that is another area of course, but medical diagnostics, several kind of instruments, electronic instruments using ferrites are used. And then magnetic materials are also used for drug delivery systems, okay, because these kind of magnetic particles can be guided through an external magnetic field inside the body of this human body, and one can place it wherever is required by applying a magnetic field. So, magnetic particles can be used. So, magnetic particles along with the drug can be actually monitored or can be delivered at a particular site with the application of the external magnetic field. So, there basically it is not the solid material, I mean it is not the bulk material, but the fine powders of magnetic materials are more of importance. Well, so far as the components are concerned, we have earlier given you the sectors of different industries, but they have some commonality so far as the components are concerned. So, these are some of the components which are used in different sectors. They have common application areas, for example, miniature transformers and motors, and including stepper motors. So, if you are talking about miniature systems of either transformers, the pot cores, or very minute or very small miniature systems or components, one can use this magnets, ceramic magnets. Radio and microwave antenna and phase shifters in the particularly the communication and also in the defense. Microwave absorbing pens for defense application, particularly some of the microwave, some of the ferrites are microwave absorbing. So, if you want to black out from a radar communication. Okay. So, one can paint it with microwave absorbing paints, and these microwave absorbing paints are nothing but some of the ferrites. Some ferrites can be painted on the surface of the metallic parts, and that is how it can be absorbed the radar waves, and therefore, it cannot be seen by the other radars. So, detection becomes difficult if it is coated with some microwave absorbing paints, and these microwave absorbing paint contains some of the magnetic materials, particularly the ferrites. Isolators and band pass filters, they are a very important component of the electronics circuits. High performance loudspeakers, ringers, they are the integral part of the current day our systems, everywhere it is used. Electroacoustic pickups, switches and relays, magnetic cards, ATM cards for example, it is magnetic tapes and discs, we have mentioned about it earlier. Magnetic sensors of different types, magneto-resistive sensors, then there are many other kind of sensors, magnetic sensors in which magnetic materials are used, NMR and drug delivery, that also I have mentioned, and so on and so forth. So, there are many different areas where this kind of ceramic magnets are essential components of our daily life or industrial activity. So, that completes our discussion on magnetic materials. Whatever little time I have, I like to discuss a couple of questions or how to address such questions. The answers are also given here. For example, the first question is calculate the magnetic moment of an isolated ion Fe2 plus. Okay. If you are, this has already been discussed to some extent, but in the details are given here. For example, how to calculate the magnetic moment of such an ion. It depends on the obviously on the d cell electrons, the unpaired electrons. Fe2 plus is actually d6 ion. So, according to Hund's rule, there are 4 unpaired electrons, okay, each having a spin of plus half, because they are all parallelly oriented. So, 2 of them out of the 6, 2 are oriented opposite to each other. So, plus and minus cancels, whereas other 4 are isolated ion, isolated electrons having plus spin, plus half spin. So, there are 4 unpaired electrons with each of half spin. So, if you try to find out what is the overall Bohr magneton of such an ion, then this was the expression given to earlier, 2 Bohr magneton into the square root of S into S plus 1, where capital, this is capital S, not the small s. The capital is the summation of all the small s's. How many small s's are there? 4. So, taking small s as half. So, the capital here becomes 4 into half equal to 2. So, S becomes 2 here. Okay. If S becomes 2, then just apply, substitute this value in this expression, and you will get the mu ion, the magnetic moment of that particular ion, which is Fe2 plus. So, 2 Bohr magneton here into root over 6 or 6 to the power half, which gives you 2.45 here and 2, so 4.9. So, the 4.9 Bohr magneton is the answer for this particular question, that is calculate the magnetic moment of an isolated ion of Fe2 plus. So, that will you can find out that this has been listed in one of the tables earlier. but I am just showing you how it has been calculated. There is one more question here. Calculate the saturation magnetization of the Fe3O4 given that this lattice parameter is 0.837 nanometers or 8.37 angstroms. Okay. So, Fe3O4 is a spinel type ferrite in which you have both Fe2 plus and Fe3 plus. So, Fe3O4 is an inverse spinel, its formula can be written as Fe3 plus, which is outside, in fact it is tetrahedral, this is tetrahedral and that is octahedral here. Okay. So, Fe3 plus is distributed between octahedral and tetrahedral. So, Fe3 plus cancels and only remaining is Fe2 plus actually. The net magnetic moment per unit volume per formula unit, actually this is per formula unit, is this is minus 5.92 because it is in tetrahedral, and the octahedral is 4.9 is for Fe2 plus and 5.92 is for Fe3 plus multiplied by Bohr magneton mu b. So, that gives 5.92 and 5.92 cancels and you have 4.9 Bohr magneton. So, for formula unit this is the 4.9 Bohr magneton. If you want to use the saturation magnetization is basically under per unit volume. Okay. So, this is how you can calculate saturation magnetization per unit volume ms equal to 8 into Bohr magneton. Okay. This is 4.9 Bohr magneton. 8 comes because this is a lattice parameter. So, the unit cell dimension is a cubic unit cell. So, the total volume of course is the unit cell is a cube is A is given, A is this value, right. So, the and 8 comes here, this 8 comes because in the unit cell of the spinel, whether inverse spinel or normal spinel, there are 8 molecules in an unit cell. Okay. So, 8 formula units are there in each unit cell, that is the reason it has to be multiplied by 8. So, 8 into one formula unit gives you this much of magnetization and divide it by the volume. So, that is how 8 into 4.9 and Bohr magneton, this is the value of the Bohr magneton, and then this becomes the volume 0.837 10 to the power minus 9 cube, because it is a cubic lattice. So, by that you can get 10 to 6.2 into 10 to the power 5 at ampere per meters. So, this is the theoretical calculation through which you can get what is the saturation magnetization of a magnetite Fe3O4. And the last question is this, number 3 question is, how do we explain the increase of saturation magnetization of nickel ferrite by addition of non-magnetic zinc oxide. Okay. In a nickel ferrite you have nickel is a magnetic material and we expect some magnetization there or magnetic moment, but when you add zinc oxide to it, that means substitute part of nickel by zinc. Zinc as such is a non-magnetic material, there is no magnetic moment here, but even then instead of a dilution effect one gets an enhancement in the magnetization, and that is quite interesting and it should be known to everybody that it may be noted. Okay, first of all, formula of nickel ferrite is like this, NiFe2O4. So, Fe3 plus again is distributed between tetrahedral and octahedral, Ni of course in the octahedral side. So, here you have the magnetic moment is arising from Ni2 plus, because this and this cancels each other, right. So, you have only that of Ni2 plus. However, in a formula of nickel zinc ferrite, you have we substitute part of the nickel by zinc, a delta amount of nickel is substituted by zinc, and that is the formula then. So, zinc is delta, so nickel 1 minus delta, but consequent to that there is some redistribution of Fe3 plus. What happens? Zinc actually goes to the tetrahedral side, it does not go to the octahedral side, although it is substituting nickel in the octahedral side, but when you are substituting it actually goes to the tetrahedral side. So, you have zinc, the number of zinc atoms in the tetrahedral side reduces, but in consideration of that, a part of Fe3 plus which was 1 here, a part of the same number of Fe3 plus as the number of zinc ions goes to the octahedral side. So, there is a transfer of iron 3 plus ions or Fe3 plus ions from the tetrahedral to the octahedral side. So, there is a disbalance here. There is a disbalance in the sense that this becomes 1 plus delta and this becomes 1 minus delta. So, earlier it was 1:1, now it has become little less than 1 and this becomes little more than 1, and this of course is less than 1, but this compensates this loss, and as a result you get a enhancement in the magnetization or magnetic moment because of this particular situation where zinc does not go into the octahedral side, although it is replacing an octahedral ion, substituting octahedral ion, but it does not go to the octahedral side, instead it comes to the tetrahedral side and it pushes some amount of iron atom to the octahedral side, and as a result the disbalance is different, or the there is no 1:1 distribution here. So, you get an enhancement in the magnetic moment. So, that is the reason, consequently the number of Fe3 plus ion increases in the octahedral side, resulting in the enhancement of the net magnetic moment. So, that is the answer to the question. So, that brings us to the discussion or the completion of the to the end of our discussion on magnetic materials. We have discussed many types of magnetic materials in general, but we have focused on ceramic magnets. So, ceramic magnets, the ferrites, the garnets as well as hexaferrites, they are the main form of ceramic magnets, and they have enormous application potential, application already being used in many different areas of sectors of industry. With today's electronics or microelectronics cannot be thought of without the use of ferrites. So, thank you for your attention.